In this paper, which is called Regression Analysis 2, we have discussed a lot of modules which deal with multiple regression. So multiple regression, in contrast to simple regression, has a number of predictor variables or explanatory variables. In one of the modules, we have discussed all the assumptions that are made when we want to fit multiple regression model, and in several other modules we have seen what happens when there is a violation of any of the assumptions that we make about a multiple regression model. In this module, we will discuss the fitting of a multiple regression to a data set which has a number of explanatory variables. We will take each piece of the output from R and we will discuss the interpretation of what the regression coefficients mean and what else we can infer about the relationship between these explanatory variables and our dependent variable y. Multiple regression can be considered as an extension of simple linear regression. There is but one difference between the two, and that is in terms of the explanatory variables. In multiple regression, unlike simple regression, there are more than one independent variables, which we denote by x. These independent variables are used to predict a single dependent variable y in both simple and multiple linear regression. Now the predicted values of y is taken as a linear transformation of the x variables if there are a number of them in multiple and if there is only one in case of simple regression. So y is taken as a linear transformation of the x variables and we subject it to the condition that the sum of squared deviations of the observed and predicted y is minimized. In other words, the sum of squared errors is minimized. Here we call error as the difference between the actual observed values of dependent variable y and the predicted values that we get as a linear transformation of the x variables. The computations in case of multiple regression are more complex due to the number of explanatory variables in the model. However, because the interrelationship among all the variables must be taken into account, the interpretation also changes accordingly. Now with two independent variables, the prediction of y can be expressed as the following expression. Y hat equals beta naught plus beta 1 x1 plus beta 2 x2. Here y hat represents the predicted value of y from a multiple regression equation using the two explanatory variables x1 and x2. x1 and x2 here are the two explanatory variables and beta naught, beta 1 and beta 2 are the regression coefficients. Now the betas are also computed in such a way that minimizes the error sum of square, where again error is the difference between the actual values or the observed values of y and the predicted values of y. So we can write the sum of squared errors as summation I equals 1 to n yi minus yi hat whole square, where yi hat is the predicted ith value of y, and we take the sum over I equals 1 to n, where n is the number of observations. This is the same form that we use or that we see when we are fitting a simple linear regression. The only difference is that in simple linear regression only two coefficients or only two regression coefficients to be specific, that is the intercept beta naught and slope beta 1 are estimated, while in case of multiple regression we estimate three regression coefficients, that is beta naught, beta 1 and beta 2. Now as the objective of this module is to look at a numerical problem where we fit a multiple regression model to the data, let us first introduce the readers to the data set that we are going to use. In the following table, we illustrate the inner workings of a multiple regression data set, where we have the variables y1, y2. These two are considered as the two dependent variables, and our set of explanatory variables are x1, x2, x3 and x4. And we have a set of observations for all of these variables, dependent and independent. Now as for the knowledge of the readers, here is a concrete description of the data file. Meaning could be given the variables as follows. Y1, which is the first dependent variable, is a measure of success in graduate school for a student. Y2, which is the second dependent variable, that gives us the score on a major review paper of the student. And the explanatory variables x1, x2, x3 and x4 are defined as: x1 is the measure of intellectual ability, x2 is a measure of work ethic, x3 is a second measure of intellectual ability, and x4 is a measure of spatial ability. Now, the first step in any kind of statistical analysis is probably to compute the summary statistics for each of these variables. So, in the next table, we analyze the multivariate data and we produce the mean and the standard deviation as well as the minimum and maximum of each of these variables. For instance, for the first dependent variable y1, we can see that the number of observations is 20, the minimum number is 125 and the maximum that this variable can attain is 230. The mean value of this dependent variable, which is the measure of success in grad school, is 169.45 and as a measure of dispersion or variability, we have standard deviation, which for this variable is 24.52. Now, since we are talking about a lot of variables, explanatory as well as dependent, we would be interested in looking at the correlation coefficient. Now, as a quick recap, correlation coefficient is a measure of the strength of the relationship between two variables. In case of simple linear regression, we find the correlation coefficient between our dependent variable y and the single explanatory variable x. Since in this study we have a multivariate data with a number of dependent variables and 4 explanatory variables, using the correlation function in R, we draw up the correlation matrix. Now, in the next matrix, this is the output from R that we get when we use the function correlation. If the reader looks at the heading of all the columns and also of all the rows, here we have the names of the variables, and along the body of this table we have the values of correlation coefficient, or rather pairwise correlation coefficient between the pair of variables. For instance, 0.31 is the correlation coefficient between the first dependent variable y1 and the second dependent variable y2, and the correlation coefficient between the first explanatory variable x1 and the first dependent variable y1 is 0.764, and so on and so forth. So, each and every value in this table can be interpreted as the pairwise correlation coefficient between the pair of variables in the data set. So, in this case of example data, it is noted that all variables correlate significantly with y1, which is depicted by the 2 stars or 2 asterisks which are put next to the values of the correlation coefficient. However, none of the explanatory variables or x variables correlate significantly with our second dependent variable, which is y2. In addition, we can also see that x1 is significantly correlated with x3 and x4 but not with x2. Now, because of high correlation between x1 and x3 and x4, we might have the problem of multicollinearity creeping in, but since we have dedicated a separate module to multicollinearity, we will discuss it later. Now, as an interpretation of the variables using the suggested meanings, it means that success in graduate school could be predicted individually with measures of intellectual ability, spatial ability and work ethic, since these are the 3 variables that are highly correlated with the performance of the student at grad school level, which is denoted by the dependent variable y1. Also, the values of the correlation coefficient tell us that the measures of intellectual ability were correlated with one another as well, and the measures of intellectual ability and work ethic were not highly correlated. The score on the review paper could not be accurately predicted in any of the other variables, since y2, which is the second dependent variable, is not significantly correlated with any of the other predictor variables. Now, in addition to the correlation coefficient matrix, we can also draw up the scatter plot of each pairwise variable in our data set. but since we have seen that y2, which is the second dependent variable, is not highly correlated with x1, x2 and x3, we have just considered the first dependent variable y1 and the three independent variables or explanatory variables which were significantly correlated with y1, and we have drawn up the scatter plot for every possible pair of these variables. Now once we figure out what the significant variables are that affect or influence our dependent variable, we can now fit a multiple regression equation or a multiple regression model to our data set, which is quite simply done in R using the LM function. But in case of fitting an LM function, the output gives us the estimates of the parameters, and the parameters involved here are the estimates of the regression coefficients beta 0, beta 1 and beta 2. Now, the formulas to compute the regression coefficients with two independent variables have been looked at before, so we will not go into that detail. Let us, however, now look at the actual numerical estimates of the parameters in this case of our example data, and then we can see how we can interpret these output. In the following table, we have these different regression coefficients in the model, and we are given the estimates of these coefficients, which is 101.222, this is the estimate of beta 0, 1 which is the estimate of beta 1, and 1.071 which is the estimate of beta 2. Along with the estimates of the parameters, we are also given the standard errors, the t-test statistic which is used to test the statistical significance of that particular variable, and also we are given the p-values. Now recalling the prediction equation which was given by y hat equals beta naught plus beta 1 x1 plus beta 2 x2, the values for the weights can now be found by observing the B column under unstandardized coefficient, which is nothing but the estimates of the coefficients. They are beta 0 equals 101.222, beta 1 equals 1 and beta 2 equals 1.071 as we have pointed out before, and using these estimates we can now rewrite our regression equation as y hat equals 101.222 plus 1 x1 plus 1.071 times x2. Now what are the residuals and predicted values of y1? Once we are able to write the regression or the prediction equation using the estimates of the coefficients, we can now calculate the residuals and also the predicted values of y for given values of our explanatory variables x1 and x2. Now the values of y1 can now be predicted using the linear transformation y1 hat equals 101.20222 plus 1 times x1 plus 1.071 times x2. Thus the value of y1, where x1 equals 13 and x2 equals 18, for the first student could be predicted as y11 hat equals 101.222 plus 1 times 13 plus 1.071 times 18, which ultimately gives us y11 hat equals 133.50. And the scores of all students are presented below in the table. Note that in the table, the predicted y score for the first student is 133.50, which we have just shown how to calculate in the slide above. Accordingly, all the other values of prediction of y are also similarly calculated by replacing x1 and x2 by their actual values. In the second last column, we have y minus y hat. This is nothing but the value of the error or the difference between the actual value of y and the estimated or predicted value of y. And in the final column, we have the square of these errors. And it is the sum of these squared errors that we minimize in order to obtain the estimates of the regression coefficients. Now the difference between the observed and predicted score y minus y hat is called a residual. This column has been computed as I have pointed out, and the analysis of residuals can be very informative. The larger the residual for a given observation, the larger the difference is between the observed value of y and the expected value of y or predicted value of y, and the greater is the error in prediction. So if after fitting a model we have very high squared errors or we have very high sum of square of errors, then we can say that the model was not a very good fit. So the larger the residual for a given observation, the larger the difference between the observed and predicted value and the greater the error. In the example above, the regression underpredicted the y value for observation 10 by a value of 10.98. So if you go back to the table and look at the 10th observation, then we can see that the difference between the actual and observed value at number 10 is 10.98 and over predicted the value of y for observation 6. So we can see the difference between the actual value of y and the observed value of y with the difference of 10.6. In some cases, the analysis of errors of prediction in a given model can direct the search for additional independent variables that might prove valuable in more complete models. So since this model which we have used to fit using the two explanatory variables x1 and x2, this was probably not a very good fit. So instead we can look at some other variables which might be influential on y. The residuals in a multiple regression are assumed to be normally distributed when the testing of hypotheses is performed. Although analysis of variance is fairly robust with respect to this assumption, it is a good idea to examine the distribution of residuals, especially with respect to outliers. The distribution of residuals for the example data is presented in the next few slides. So let us look at first the multiple correlation coefficient, which is also a part of the R output after fitting a multiple regression equation. So the multiple correlation coefficient, which is denoted by R, is the correlation coefficient between the observed values of y and the predicted values of y. Now for this reason, the value of R will always be positive and will take on a value between 0 and 1. And the detection of the multivariate relationship between the independent and the dependent variables can be observed in the sign positive or negative of the regression weights. What this really means is, if x1, which is the first explanatory variable, positively influences the dependent variable y, then there will be a positive sign attached to the corresponding regression coefficient beta 1, and if the second variable x2 influences y in a negative manner, then we will see a negative sign attached to our regression coefficient beta 2, and so on. So the interpretation of R is similar to the interpretation of correlation coefficient for a pair of variables. So the closer the value of R is to 1, the greater the linear relationship between the independent variable and its predicted value. So the multiple correlation coefficient R square is also called coefficient of determination. In this model, we have seen that the value of R square is 0.936. So the interpretation of R square is similar to interpretation of small r square, namely the proportion of variance in y that may be predicted by knowing the value of x variables. Now, as I have mentioned before, uppercase or capital R square is an estimate of the correlation between y and the predicted values of y. So if the x's or the explanatory variables are highly correlated with y, in such cases the model is going to give a very good fit, and if the model is a good fit, then the predicted values would be very close to the observed values, and thus it will in turn increase the value of R square or uppercase R square, which is the coefficient of determination. So the interpretation of coefficient of determination or uppercase R square can be considered similar or equivalent to the interpretation of correlation coefficient or correlation between x and y. The adjustment in the adjusted R square value in the output table is again a correction for the number of x variables included in the prediction model. One of the features of a multiple regression model is that as you keep increasing the number of explanatory variables, the R square for the model will always increase, but sometimes this increase is not statistically significant. If this increase is not significant, then inclusion of a new variable will only increase the complexity of the model and also will increase the number of parameters that we have to estimate. So in order to put a check on the number of variables or explanatory variables that we add in a model, what we do is we calculate an adjusted R square value. which is adjusted for the number of parameters or the number of x variables included in the model. So this is the calculation of r square adjusted for the number of parameters p. So even if there is an increase in r square, the increase is not significantly reflected in the adjusted r square, and thus we can decide on whether we want to include a new variable or not. In general, the smaller the n and the larger the number of variables, the greater is the adjustment. So as we have smaller number of observation, which is denoted by n, and there are large number of variable x's, so the number of regression coefficient also increases. In this case, a greater adjustment is needed to be made. In this example, the results could be reported as 92.9% of the variance in the measures of success in graduate school can be predicted by measures of intellectual ability and work ethic, which were the two explanatory variables that we had used to explain our y variable, which was the measure of success in graduate school. So in this module, we have seen that if we use R to fit a regression model, what are the different parts of the output, and also if we have a data set to begin with which has one dependent variable and several explanatory variables that this variable depends on, then we have several different statistical coefficients that we can calculate to see the strength of the relationship between these variables and the dependent variable. We will discuss several other features of fitting of a multiple regression model to a data set in the next module, which is a sequel of the one which we have currently discussed.